Hi, today we're going to go for another quick bit where we focus on the geometry of measurement statistics in non-signaling scenarios. So last time we discussed the Clauser-Horn-Shimoni-Holt or CHSH scenario. Basically, Alice and Bob each have access to some black box, and they are allowed to push two levers, X0 or Y, X0 or X1, Y0 or Y1, and they get some 0 or 1. Every time they do this, some referee puts together their outcomes 0 or 0, and these form a sort of four possible outcomes 0 0 0 1 1 0 1 1, and that's associated to each time they pick a distinct set of inputs. They repeat this over many trials, and they tabulate some statistics. And then they can therefore estimate some probabilities based on the frequency with which these outcomes occur. However, we're not allowed just any old set of probabilities. They have to satisfy this non-signaling principle. This non-signaling principle is motivated by Einstein's special relativity. Alice and Bob are distantly separated, so it should be the case that Bob's choice of input should not affect Alice's outcomes and vice versa. How does this work mathematically? It works in the following way. So all Alice ever sees is her zeros and ones. So remember, the 0 0 0 1 1 0 1 1 is only observed by the referee who tabulates these outcomes. So all Alice ever sees is either 0 or 1. Now, for a particular setting where Alice chooses one of her measurements and Bob chooses Y0, the probability that Alice gets 0, which would be this, is going to come from marginalization by adding up the probabilities in which Alice has 0. So here, probability that Alice gets 0 is probability of 0 0 plus probability of 0 1. So that's the sum of these top rows. And similarly, Bob could have chosen Y1 instead of Y0. And similarly, these two numbers should add up to be this number again. Again, individually, these numbers may be all distinct, but their sum has to be the same. Similarly, for the bottom row. And when they satisfy this sort of marginalization constraint, we say that they satisfy the principle of non-signaling. And when that happens, we sort of glue, for lack of a better term, these cells together. In fact, that'll be a sort of notion that we use later on in the simplicial approach. So this is sort of an interesting thing because we're going to be able to distinguish between probability tables that come from something we call classical, and everything that's not classical is non-classical. So what is the definition of classical? It's when Alice and Bob can associate to each of their inputs. So when they pick one of these inputs, they get an output. If we can say that that input corresponds to measuring some element of reality, then we can assign some sort of physical item out in the world which corresponds to that particular input. So in this case, we have four possible inputs, and so we can think of these boxes as measuring four different coins. Alice can measure one of two, Bob can measure one of two. They never see, as part of the game, they never see all four coins at once. That's what makes this all non-trivial. All you can ever see is just you pick one or the other. But nonetheless, if you have this assumption of realism, that there is some physical object out there in the world, it's the case that even if you can't measure all four at the same time, they nonetheless have values. These four coins are either heads or tails or 0 or 1, depending on your perspective. And in this case, we are also assuming locality in the sense that Bob's choices don't affect Alice's outcomes and vice versa. So we talked about this last time. There's 16 possible choices, 2 to the 4 possible choices of deterministic distributions. This is just definite assignments of heads or tails. But we call a classical distribution anything that's a probabilistic mixture of these. Just like you can have a probabilistic mixtures of heads and tails, you can have a situation in which the physical scenario underlying Alice and Bob's setup is one that with 50% gives you all heads or 50% gives you all tails. It could be some sort of weird machine like this, or any generic probabilistic mixture. The set of all possible statistics consistent with probabilistic mixtures of these types of tables is called the Bell polytope, or the CHSH polytope in this case, to be more specific. Okay, but we want to talk about this in a little bit more abstract way. And we want to delve into the geometry of these sorts of measurement statistics. So for that, we're going to need to talk about, at least in an informal sense, we're going to need to talk about polytopes. So in an informal sense, to repeat myself, a polytope is going to be an object with flat surfaces. Okay, we can make that a little bit more precise, and pointed corners and bounded. So a cube or a tetrahedron are good examples of these. Something that satisfies the first two, for example, is like the positive orthant of a coordinates of a Euclidean or of a Cartesian coordinate system, right? Because it has flat surfaces, just the faces of the coordinate system, and it has a pointed corner, but it's not bounded. It goes off to infinity. So roughly speaking, these flat surfaces, so looking at this square right here, which is like a 2 cube, the flat surfaces come from inequalities. I can have x be greater than -1 or below +1, or I could similarly have y be less than +1 or greater than -1. And the region that intersects all of these constraints is what we call the square. Now, the sharp corners, I will give a even less precise definition of this, but more or less we can see that it's where you have an intersection of these faces. In the case of the square, the faces, we have a two-dimensional space, the square itself, and its faces are one-dimensional. The intersection of those one-dimensional spaces is where you get these vertices, which we can see with the cube as well. In fact, the ability to go between describing a polytope between these flat surfaces and pointed corners is a very basic fact about polytopes. The Minkowski-Weil theorem gives that, but we're not going to get into that. So let's give a slightly more sophisticated example that maybe we haven't seen before, the probability simplex. Now, we're going to discuss simplices in a different sort of from a different perspective later on, but here the probability simplex, we mean precisely the definition that I'm giving here. It's got a precise geometry. Suppose, for example, we have, well, this is one example of a probability simplex at least. We have three possible outcomes, 0, 1, or 2. A realistic situation for this would be like taking a six-sided cube and then grouping together 1 and 2, 3 and 4, 5 and 6. And then you roll the dice, and whenever you get 1 or 2, that's outcome 0. Whenever you get 3 or 4, that's outcome 1. Whenever you get 5 or 6, that's outcome 2. And then there's some probability of these occurring. In a fair die, these would all be 1/3, for example. But 1/3 is going to end up being something that's directly in the middle of our probability simplex. Now, how do we describe the appropriate polytope that corresponds to such a situation? Well, we have that our probabilities are always greater than or equal to 0. On its own, this leads to a sort of cone where you have one vertex at the origin, and then you have that all of the coordinates go off to infinity. We can take the x, y, and z coordinates to be p0, p1, and p2, and then all that you're requiring is that they're greater than or equal to 0. This is just a positive quadrant. But of course, probabilities need to also be normalized, because there's the probability that any outcome occurs should be 1. And when we do this, we cut this cone by a surface, a two-dimensional surface, this one. And then, so we have now a polytope, a two-dimensional convex space. It's got corners, and the flat spaces here are the edges of this triangle. So this is an example of a polytope as well. And you can see that a polytope can be obtained by inequalities plus equations which cut these sort of, in general for us, the inequalities will be probabilities greater than or equal to some greater than or equal to 0, and then the equalities cut it so that it's bounded. So non-signaling polytopes. Let's consider the simplest possible case. Alice and Bob each have one possible input. So if they have one possible input, then I can just write down one cell like so. And here, the non-signaling polytope will be obtained by taking each of the parameters here. There's 4 possible probabilities. They each must be greater than or equal to 0. Unassigned piece of homework: find the vertices of this probability simplex. Okay, so back to here, we have four inequalities, one for each of the outcomes, and we have an equality because, of course, all the probabilities in this cell are all the outcomes are mutually exclusive, so we have that their sum should be equal to 1. And secondary exercise: find the vertices of this polytope. Now it's very related to the previous one, just one dimension up. In fact, you should be able to draw the space. In fact, yeah, you could even draw the space for this particular probability simplex, which is also a non-signaling polytope in this case. Okay, let's get a little bit more sophisticated. Let's look at the non-signaling polytope, or at least in principle, how you would construct the non-signaling polytope for the CHSH scenario. Here, we have that there are 16 parameters. Every probability that occurs in this table should be greater than or equal to 0. And there's 16 such parameters. But that's not enough. We also have that in each cell, the probabilities must be normalized. This is enough to actually cause the non-signaling polytope to be bounded, because if you have numbers that are non-negative and they sum to 1, then they have an upper limit, namely that they're between 0 and 1. So that's like saying that that you will always have something like a cube in the positive orthant of your space. So in principle, you can take each of these probabilities to be a coordinate in some Cartesian coordinate system, and then you will have that just based on this and the normalization, it will be like a cube in that positive sector. But that's not it. We also have non-signaling constraints. You also have to input that these two numbers equal these two numbers, and then these two numbers equal these two numbers, so on and so forth. Previously, when we looked at, for example, it's more apparent here, just the inequalities gave us, we had a 3-dimensional space of possible probabilities, just if you look at these. And then you add an equality, equation constraint, and it reduces it to from 3 to 2. Now, one might surmise that every time I have an equality, it reduces the dimension, the number of independent variables by 1. So, but I'm not saying that that's the case. I'm just asking as a second sort of exercise, what is the dimension of this polytope? If I naively apply the formula that I used before, I have 16 minus 4 normalization constraints minus 4 in the blue minus 4 in the red equals 12. Now, is that the right answer? Clearly, if I'm asking it, then it's probably not. So just go ahead and see what the actual dimension, sorry, I said 12 before, but that would give me 16 minus 4 minus 4 minus 4 equals 4, which is not correct. So what we have is that we have this non-signaling polytope, and we previously discussed the classical Bell polytope. So as a general feature of non-signaling polytopes, like the ones I've just described, it's going to be the case that they have these blue vertices will be deterministic distributions. These are always vertices of this non-signaling polytope. But there could be other vertices. And so what is the significance of that? So what we see is that when I take the probabilistic mixtures of the blue vertices, it's going to be like a subset of all possible non-signaling distributions. Non-signaling distributions are all these, and then the classical one will be some subset of that. What that means is that there are going to be points inside that satisfy non-signaling. So what that means is that there will be distributions that are non-signaling, but they're also non-classical in the sense that they are inside the non-signaling polytope. Now I've picked a particular vertex. This is a PR box that I mentioned last time, but it could also be here, here, or wherever. So they're non-classical because they're outside of this region, but they also satisfy non-signaling. So clearly non-signaling is itself not enough to restrict you from is not enough to impose classicality. So there's another sort of region that we could be interested in, which is the quantum region. So in general, so this dotted red line could be all possible, everything that's inside there could be all quantum statistics. For example, this distribution right here, this is coming from a paper from Abramsky and Brandenburger. In 2011, I believe. And so there are quantum statistics that can exceed these classical bounds, but they're always inside the non-signaling polytope. Now, it turns out that the quantum statistics sometimes don't ever reach the outer vertices of this non-signaling polytope. Sometimes they do. There are cases where that happens. But in general, the quantum correlations are a subset of non-signaling correlations. So you can sort of picture it in this sort of hierarchy. You have classical correlations, and then quantum correlations include classical correlations, but some more, and then non-signaling correlations or distributions, and I'm using those terms interchangeably, kind of encompasses all of them. It's sort of the least constraining principle. So hope that was useful. Next time, I think that we can go in a couple of different directions here. I think that I'd like to do a little lecture where we can sort of implement or look at the vertices of such polytopes, and maybe I'll have a little template and a Jupyter notebook where people can sort of mess around and compute these the vertices of these polytopes given the faces and the equations. And another direction that we'll go in is to introduce the simplicial approach to quantum non-locality and contextuality, which sort of builds on these ideas. Okay, thank you.